All right, so on this sheet, we're going to start balancing. We're going to do numbers. We're going to start with number 7. We've already done all the previous ones. All right, so let's look at this. Now, what type of reaction did you write down for this one? Single replacement. Okay, so tomorrow we're going to just focus solely on single replacement reactions, and you're going to see how simple they really are. But remember, and if you want to write this down, remember I told you something. We have to look at something to determine if lithium can kick lead out. Now, because this reaction worked, did lithium kick it out? Yes. The sheet we're going to have to look at tomorrow is this one. Again, you'll get it tomorrow. Sam, can you see what is the top element on that list? No, the top one up here. Lithium, okay? So according to this, remember I said this is kind of like the hotness scale? Who is the hottest thing on this list? Lithium, okay? It is the most active element on the periodic table. Now, Sam, can you tell me who the bottom one is? I think it's kind of funny. It is gold, okay? So gold is the least active element, so it's never going to swap with anybody, okay? All right, so in terms of balancing, let's look and see what we've got. So how many Li's do we have on our left? 1. How many Li's do we have on our right? We're good. All right, how many leads do we have on our left? How many leads we got on our right? 1. We're good. But again, when you get to polyatomics, you have to determine are the polyatomics on both sides. And first of all, what is the polyatomic that you see? Hydroxide, okay? And then is it on both sides? Yes, okay. Well, how many do I have on the left-hand side? 2. How many do I have over there on the right? And again, if you look right here, it's just one OH group. Well, that's a problem. So I need to put a 2 here. Now, could you circle your answer and say you're finished? No, because what else had that just changed? That changed lithium. So let's come back over here, and I need to put a 2 right here. So would that be your final answer? Yes, okay. And again, how you would report that would be 2, 1, 1, 2. 2, 1, 1, 2. We cool with that? Okay. All right, moving on to number 8. Did we balance number 8? All right, so let's look at number 8. First of all, what type of reaction did you write down? Combustion. This is combustion. And I gave you 3 very simple rules for combustion. I hope they're still there. Yeah. Nope. Somebody erased them. Dad darn it. I think I wrote them down. Yeah, there they are. Okay. So, what's the first thing that you do? All right. In your example, what is the hydrocarbon? Okay, so put a 2 in front of it. Okay. Going back to the rules, what's rule number 2? Balance is needed. Now, let me ask you something. When is the only time you double the hydrocarbon? When it's a combustion reaction only. Okay? Only when it's combustion. All right, so we're going to balance as needed. So that gives me how many carbons on the left? Gives me 8. So I need 8 carbons over here. Okay? Now let's move on to hydrogens. How many hydrogens do I have on my left? 16. How do I make it 16 on the right? Put an 8. Now this is where you got to do a little bit of math. All right, so let's look at oxygens on the right-hand side. So how many oxygens do I have in CO2? How did you get 16? 8 times 2. Now, how many oxygens do I have in my water? I've got 8. And this is very important. What mathematical symbol is between those two formulas? A plus sign. So what do you do to 16 and 8? You add them. What is 16 plus 8? 24. So I've got 24 total oxygens on my product side. How many, as of right now, do I have on my reactant side? 2. What's half of 24? 12. And this next step is the most important step. And again, I'm going to go back to the rules. What is that last step? Reduce if you can. So look at all of those numbers. Now, and every year I have this issue. Do you reduce? All right, let me figure out the best way to ask this question. Can you just reduce only certain numbers, or do you have to reduce all of them? All of them. Every year I get people who just reduce certain ones. Now, if you can reduce, you have to be able to reduce all of them. And are all of them divisible by a certain value? Yes, they're all divisible by 2. So that turns into a 1, that turns into a 6, that turns into a 4, and that turns into a 4. So that's your final answer. Okay, that is your final answer. Anthony, are you with us? Put them up. Put them up. All of them. Okay. All right, let's look at number 9. What type of reaction is number 9? Double. Now, here's the deal, and again, I'm throwing this at you. Why is this not an acid-base reaction? What part of the acid-base are you missing? You're missing the acid. Okay, it has to be both of them. You're missing the acid, so let's go ahead and start. All right, so let's start with gallium. So how many galliums do I have on the left? 1. How many galliums on the right? 1. Good. Now, remember, we're going to save the H's and O's for last, so we're going to move over to potassium. How many potassiums on the left? 1. How many potassiums on the right? 1. You're good. All right, how many fluorines are on the left? On the left. 1. How many on the right? 3. Well, I can't have that. So what do I do to make them balance? Okay, I need to put a 3 right there. Now here's the deal. That did not just affect my fluorine, that also affected my potassium. So do I need to go back and change the potassium? Yes, so what do I now need to put in front of the potassium on the other side? Put a 3. And magic just happened. Why? Because that finished my problem. Now do you see why we save those big crazy ones for last? Because if we take care of the smaller ones first, sometimes it goes ahead and takes care of the bigger ones. And what am I talking about? That 3 just gave me 3 potassiums and 3 what? Hydroxides. Well, how many hydroxides did I have on the reactant side? 3. So I didn't have to even think about it. I just kind of went through it. Now some of you are going to say, well, I've got 3 hydroxides, I've got 1. I know I need to do that. It doesn't, there's not a particular order you have to go in. I'm just trying to train you on the best order to go in. All right, let's look at number 10. All right, how many, first of all, what is V? Vanadium. Vanadium. How many V's on the left? 1. How many V's on the right? 1. You're good. How many ZNs on the left? 1. How many ZNs on the right? 1. How many BRs on the left? 2. Okay. And how many BRs on the right? 3. Remember I taught you a rule when one of them is a 2 and one of them is a 3. What was that rule? The 2, 3, 6 rule. So the lowest common multiple between those two is 6. So if you see a 2, what do you put in front of it? Put a 3. If you see a 3, what do you put in front of it? A 2. Now, that just became a little more aggravating, but it's super simple. What do you have to now put in front of the single V? You got to put a 2, and over there on the other side, you got to put a 3. So your reported answer should be 2, 3, 2, 3. Does that make sense? All you're doing is literally writing the coefficients in a sequence. By the way, what type of reaction is that? Single replacement. I would go ahead, and I'm going to go ahead and tell you this. I would not give you this test, this question on the test. And the reason why is, what would we have to know about vanadium compared to zinc about this list? For it to work, does vanadium have to be above zinc or below zinc on this list? This is a hotness scale. Above zinc. Well, the problem is vanadium is not on my list. But since it worked, what can we assume? That it is above. Okay, and tomorrow we'll talk about what elements go where, and we'll kind of see it from that perspective. Okay. All right, so let's move on to the next one. So AS2O5 plus water yields arsenic acid. So how many AS's do I have on my left? 2. How many do I have on my right? All right, so again, if we have 3 hydrogens, we've got 1 AS, and we've got 4 oxygens. So this is going to be a little challenging. So I'm just going to put my 2 in front of this. Does that make sense? So here's the deal. Let me ask you something. Do you agree that the only thing we're left with is H's and O's? Which one would you try to balance first? The hydrogens or the oxygens? Why the hydrogens first? Can I give you a very simple clue of why? Look on the reactant side. How many locations, or how many formulas or compounds is oxygen a part of on the reactant side? It's a part of both of them. But what about hydrogen? How many is it a part of? 1. Do you agree that it's a lot easier to solve for 1 than it is to solve for 2? So let's do the easy one first. All right, so how many hydrogens are on the reactant side, or on the left? 2. How many over there on the right? 6. There's that rule again. So what do I need to put in front of the water? I need to put a 3. Now let's see what that did to my oxygens. Let's look at the reactants. Actually, let's look at the product side first. It's easier math. Why is it easier math? All you have to do is just distribute that too. So how many total oxygens are on the product side? 8 of them. Okay. Now let's go back over here. So in AS2O5, how many oxygens are there? There are 5 plus how many oxygens in the water? 3. Well, what's 5 plus 3? So you're balanced. You're good. It's done. So 1, 3, 2 would be your final answer. 1, 3, 2 would be your final answer. Go ahead. No, sir. Absolutely not. Because, in fact, you're technically kind of more correct with it there than without it there. But it's just very much understood to eliminate the 1. Okay. But no, if you write it, that's fine. If it makes you feel more comfortable writing it, go right ahead. Okay. All right, let's look at number 12. 12 may throw us for a curveball, but we can figure it out. Let's just... You know what? Actually, I'm going to take it from you guys, from your approach, and let's see if in my mind, I'm going to do it a little bit differently. So let's start with ends. How many ends on the left? 1. How many ends on the right? 1. All right. How many hydrogens on the left? 3. How many hydrogens on the right? Uh-oh, we're in trouble. So what do I have to do? All right, so that's my 2, 3, 6 rule, right? So if I put a 2 here, put a 2 in front of the ammonia, NH3, and what goes in front of the water? 3. Everybody okay with that? Now, since I put that 2 in front of that ammonia, what did that just do? That gave me 2 ends. So now I need to put a 2 right here. Do you agree? All right. So let's see what's wrong. So let's just count. Let's make sure. So I've got how many oxygens in NO? I've got 2 plus how many in water? 3. What's 2 plus 3? 5. Uh-oh. What's wrong? You can't. Say that one more time. So if you can't get it to make 5, could you possibly get it to make 10? So let's try that. Let's see what happens. So let's double everything. So we're going to change this to 4. We'll change that to 4. And we're going to change that to 6. And let's see if our numbers change. Let's see if our numbers change. Now, do you agree that nitrogens are still 4 and 4? How many hydrogens do you now each have? You've got 12 each, right? All right, so let's now look at our oxygens. How many oxygens are in NO? 4. Okay? Plus, how many oxygens are in water? 6. What is 4 plus 6? 10. Well, can I get 10 out of 2? What do? Put a 5. And that's your final answer. So, here's the rule. Will you let her in, please? So, here's the rule. If you get to a part where an odd number shows up. Yes, ma'am. Slacker. What is in that thing? Bricks? Is it? I would agree with that. So here's the rule. If you ever come to a point when you've got an odd number that you can't make it balance, what do? Double everything and then retry to balance it. Okay, so that's going to be your rule. All right, so did everybody get that one? Everybody done with this? Have we finished all of them now? All right, so here's what I want to do. Since I heard some of you say that, you know what, the balancing part is okay, but I'm not necessarily sure how to identify reactions. If you guys will flip over, and as I'm finding it on my files, just go ahead and do all 15 to the left and just put the letter of the type of reaction. That's all I want you to do. Just put the type of it. So combustion is C, acid base is AB, synthesis is S, decomposition is D, single replacement is SR, and double replacement is DR. Just identify it for right now. All right, so let's go ahead and go through these. Now, number 1 probably kind of threw you for a loop because you look at it, you say, well, all right, H3PF4, that's an acid. HCl, that's also an acid. So is this an acid-acid? No, there is no such thing. But what this is what? It is a strange, weird double replacement reaction. Okay? It is a double replacement. Because what happens is when these two things actually react, and I'm going to be 100% honest with you, this is going to be aqueous, I would assume, and this is more or less probably going to be a gas, but we're not going to get into that. But the phosphorus actually reacts with the chlorine, and it creates a double replacement. All right. Number 2, you've got CaC2 plus water yields C2H2 and calcium hydroxide. So what type would this be? This is also a double replacement in a weird, strange, odd kind of way. This is the stuff that, due to time constraints, we're not going to be able to get into, but that's okay. As long as you can still recognize what's kind of happening, then you're fine. Yes, sir? Only produced by acid-base reactions. No, and I mean, all right, so think about it. All acid-base reactions produce a what and a what? A salt and a water. Well, the two products, one of them's a water, the other one has to be the salt. You have to have an acid-base reaction. There's no other way to identify it other than the fact that it's... I'm not going to ask you to do that. All right, number 3, this was really easy. What type you got? Decomp. Number 4, what you got? Decomp. Number 5 is a weird, strange, odd kind of thing. Remember I told you, I wrote this right here, and I said that CO2 and H2 are always the products. And I told you that this is technically a little white lie, that not every single 100% of the time that this is always true, but for your need-to-know knowledge basis, it is. And I've kind of thrown 2 at you just to prove that it's not 100% of the time, because this thing right here kind of throws it off. But if you think about it, this stuff that's this hydrocarbon is ethanol. And what is ethanol used in? It's in your gasoline that's in your vehicle. And what is the gas that your vehicle produces that's so dangerous? Carbon monoxide, which is exactly what that stuff is. So this is a real-life engine-burning reaction, okay? But this is combustion. All right, number 6, what type you got? Synthesis, very good. Number 7, single replacement. So let's look at this real quick. All single replacement reactions need a what? You have to use the what? Look at what? The activity series. Since this reacted, what does that tell you about calcium versus aluminum on that list? Calcium is higher on that list, and we'll look at that tomorrow. All right, number 8, what type you got? Decomp. Number 9, decomp. Number 10, decomp. Wow. Number 11, combustion. Now, number 12 is a little funny. Kind of got to look at it. What is number 12? Single replacement. So since carbon kicked iron out, what does that tell you about carbon? It's more active. Okay? All right, number 13, what you got? Single replacement. Okay? The reason it's single is, notice what happens. Iron's with a compound, and then what happens to iron on the other side? It's kicked out all by itself. Okay? 14, what you got? Combustion. And 15, what you got? Combustion. Very good. So let's go back and let's look at balancing these things. All right, start with number 1. Remember, save the what and what for last? H's and O's for last. So we're going to start with P. So how many P's do you have on the left? 1. How many P's you got on the right? 1. How many H's do you have? Excuse me. How many Cl's do you have on the left? How many Cl's you got on the right? 5. So where do I put my 5? On the left. Now we've got H's and O's to deal with. Now think about this. Which element is going to be easier to balance, the oxygen or the hydrogen? What do you see less of? You see less oxygens. Okay, so let's start there. So how many oxygens are on the left? 4. How many are on the right? 1. So I put a 4 in front of the water, right? We cool with that? All right, now how many hydrogens did that give you on the right-hand side? That gave me 8. Now let's go back over here on the left side and actually calculate. All right, how many hydrogens are in H3PO4? There are 3 of them. How many hydrogens are in HCl? 5. Well, what is 5 plus 3? 8. So are you balanced? Yes. So how would you write your answer? All right, so you can just say it all out. 1, 5, 1, 4. Does that make sense? Okay. All right, let's do number 2. C2 plus water plus C2H2 plus calcium hydroxide. Save the what and what for last? H's and O's. Okay. So I've got one Ca, and how many over there do I have? One, so I'm good. I've got two C's, and I've got two C's. All right, now we're down to H's and O's. Which one's possibly going to be easier to balance? O's. Now here, let me talk about something. Do you see a polyatomic? Who is it? Hydroxide. But the problem is, do you see it on both sides? No. And this is very important. When and when only can you change water to HOH? Acid-base and acid-base only is when you can change water to HOH. All right, so let's start with the oxygens first. All right, how many oxygens do I have on the left? One. How many over here do I have? Two. Because you remember, we're not going to count that as hydroxide. We're going to count it as an individual oxygen. So I've got two there, so I need to put a 2 here. Are we cool with that? All right. Now how many hydrogens does that give me on my left? 4. Now we got to add them all up over there on the other side. So how many hydrogens are in C2H2? There are 2 of them. How many hydrogens are in CaOH2? There are 2 of them. What is 2 plus 2? 4. So is it balanced? Yes. So the way you would write your answer is 1, 2, 1, 1. Cool with that? All right. Look at the next one. Number 3. How many FEs on the left? 1. How many FEs on the right? 2. That's a problem. What do I need to do? Put a 2 where? In front of the FeOH 3. So this is going to give me a 2. All right, so now we need to figure out which one's easiest to balance, because can you use hydroxide as an entity? No, because you only see it on how many sides? One side. So how many H's do we have on the left? Be very careful here. You've got to distribute. You've got a 3 and you've got a 2, which gives me how many? 6. Well, how many hydrogens do I have in that water? I've only got 2, so what do I put? Put a 3. Everybody okay with that? Okay. Now, let's count up our oxygens. How many do I have on the left still? Still got 6, but how many oxygens are in Fe2O3? There are 3. How many oxygens are in water? 3. What's 3 plus 3? 6, so it checks off. We good with that? All right, since there's a little bit of time left, I know there's very little, I want to make sure that you guys can do that half-sheet homework, because look at that real quick. I want to make sure that you can do that before you start trying to balancing it, because there's going to be 2 of these problems on the test just like this.